Alright, so with the linear algebra of G2 out of the way, we can talk about instantons. So let's go talk about ASD instantons and G2 instantons. And to this end, we always need some principal bundle over a manifold X. Let's say with structure group G. And we will be looking at principal bundle connections. So let A be a one form on P with values in the Lie algebra of our group G. And we ask that this be a connection on P. So it does have some invariance properties, but for now it's fine to just think of it as a one form on P. Right, then in dimension 4, you say that, so if the dimension of X equals 4, you say that A is an ASD instanton if the following is true. So let's say omega 1, omega 2, omega 3 is a hyperkähler triple on our 4 manifold. Then we ask that Fa, which omega I equals to 0 for I equals to 1, 2, 3. Now, this ASD here, that means anti-self dual. And the reason it's called anti-self dual is that there is another equivalent and maybe even more commonly known definition of ASD instantons. And that alternative definition is that one asks that star Fa equals to minus Fa. And that's the very classical story of instantons in dimension 4, and that's exactly the objects that are used in Donaldson theory to define the invariance of smooth 4 manifolds. But now what can we do in dimension 7? So we have that dim x equals 7, and let's say we have some G2 structure phi. Well, the definition that you make in this case is, you say that A is a G2 instanton if Fa, which star phi equals to 0. So this kind of mimics this first definition of ASD instantons here. But if you want, you can also mimic this second definition here. And where you want to write Fa equals to, you want to write star Fa equals to minus Fa, but it doesn't make sense on a 7 manifold, because now the left-hand side of your equation is a 5 form, and the right-hand side is a 2 form. So the correct analog of this ASD equation for G2 manifolds is that you wedge with phi here. And it turns out that these two definitions are equivalent. But again, for practical purposes, the yellow definition is more suitable than the blue definition. So what are examples of G2 instantons? Well, the whole point of the lecture is to construct interesting examples of G2 instantons, but we have two simple examples that we can write down right away. The first one is just flat connections. So if A is a flat connection, so that just means that the curvature vanishes. Well, if you look at the yellow definition, it's definitely always going to be true, because it doesn't matter what you wedge FA with, it's always certainly going to be 0. So flat connection definitely is a G2 instanton. Okay, maybe that example was a bit silly, but we now have a more substantial example, and in fact we're going to need exactly this example later on in our real construction. So let me write that as a proposition. If P, a map from T3 to X, let's say Iguchi-Hansen space, to X Iguchi-Hansen space, even though it doesn't matter that it's Iguchi-Hansen space. It could be any hyperkähler manifold, but we've only seen that one hyperkähler manifold, so let's stick with it. So if that's the projection onto the second component, and if A is an ASD instanton, over Iguchi-Hansen space, then P star A is a G2 instanton on T3 times X. Alright, so why would that be the case? Let's look at the proof of that. Well, first, it's a quick linear algebra computation to compute what is star of phi product. And you just take the star of each of these summands in the definition of phi product, and what you'll get is the volume form of X minus, and then gets a bit tedious to write, but I'll try my best. Ijk is equal to 1, 2, 3, or cyclic permutations of that. So 2, 3, 1, 3, 1, 2. And then what we sum is dxi, which dxj, which omega k twiddle, where omega k twiddle was the hyperkähler triple on Iguchi-Hansen space. So now what we have to check is what's the curvature of P star A, wedge star phi product. Now, what we're going to use throughout is that f P star A is the same as P star of FA. And if we have this and plug in the definition of phi product, what you'll get is P star of FA, which the volume form of X, minus, and then this complicated sum here, over dxi, which dxj, which, and then P star of FA, which omega k twiddle. Alright, and now what do we see? Well, this first guy here, this FA wedge wall X, well, that's a 6 form on a on a 4-dimensional manifold. So it must vanish. And what do we see for this last term here, for this FA wedge omega k twiddle? Well, that this guy vanishes is exactly the ASD condition for A. So we have that this is 0 because A is anti-self-dual. So overall we have that the whole thing is 0. So that's the first slightly non-trivial example of a G2 instanton. Right, so with this all set, we can jump into the most exciting part of this lecture, which is the construction of a G2 instanton on a compact manifold. And well, first I'll spend some time explaining on which manifolds this takes place. So to this end, we start with T7, the 7 torus, and we define the map alpha from T7 to T7 as follows. So this vector of 7 numbers, so given such a vector of 7 numbers, we multiply the last 4 coordinates by -1. That's what this map does. So it's x1, x2, x3, minus x4, minus x5, minus x6, minus x7. And I'll explain the construction using just this map alpha here. In reality, in Joyce's construction, he needed 3 maps. He needed alpha, beta, and gamma. And then resolve the quotient of T7 mod alpha, beta, and gamma. The reason I forget about this beta and gamma here is the analysis for beta and gamma is the same as for alpha, so it just makes all the explanations a bit longer, but you're not really missing out anything if you just talk about alpha. But you should know the truth, and that is if you do literally the construction that's written here, so with just one map alpha, in the end you'll get something with holonomy contained in G2, but not equal to G2. So to beef it up to something with holonomy equal to G2, you really do need these extra maps, beta and gamma, that I will not talk about. They do look very similar to alpha, they have the minus signs in different places. Good, so let's forget everything about beta and alpha, beta and gamma, and let's just look at alpha. With this nice little map alpha here, you will find that the fixed point set of alpha is 8 copies of T3. So for example, you can take the last 4 coordinates to be equal to 0, and you can put anything in the first 3 coordinates, and that's exactly one of those T3s. Now, let's just focus on one of the T3s. You do the same to each of the 8 T3s. So let's zoom into one of them. For one of them, or for each of them, there exists a neighborhood U of T3 in this quotient space, T7 mod alpha, such that U is isometric to T3 times B4 mod plus minus 1. And now what we'll do is we'll take our space T7 mod alpha, cut out the U, and glue in something smooth instead. And that smooth thing will come exactly from this Iguchi-Hansen space that was explained before. So here's the picture. Here we have our singular space, T7 mod alpha, with a bunch of T3s living in it. And around each T3, we have a neighborhood U, which is isometric to T3 times B4 mod plus minus 1. Now, what we can do is we can map onto this yellow set here by taking the identity on T3 times this Iguchi-Hansen blow-up map from before. That was called pi. So let's call these two maps together rho, because we sometimes need that. So up here we have T3 times XEH, which kind of looks like this. And there our yellow set corresponds to some green set, the pre-image under rho. And so what we can do now is we can glue, and we end up with our T7 mod alpha, but the yellow set cut out and the green set pasted in. So in formulae, this manifold here is N, defined to be the thing we started with, T7 mod alpha, but without the fixed point set. And then glued together to this green set here, to rho inverse of U, glued exactly again along rho. Now, that's just all as smooth manifold. So far nothing has been said about G2 structures. But the G2 structures come now. Because the interesting thing is that on this glued together manifold you have two G2 structures. First, from the torus you have the flat G2 structure phi 0. Remember, I wrote down the G2 structure phi 0 on R7, but that immediately defines you a G2 structure on the 7 torus T7. It's left invariant by the map alpha, and so you get a G2 structure phi 0 on T7 mod alpha. So wherever you didn't do the gluing, you still have this G2 structure phi 0. But now in the region where you did do the gluing, well, there you have the G2 structure phi product that was written down before. So you have these two torsion-free G2 structures, phi 0 and phi product, and the question is, can you somehow glue them together to one G2 structure that's torsion-free everywhere? And the answer is yes. And that was the big achievement by Dominic Joyce in his 94 paper. So there he found there exists a torsion-free G2 structure phi twiddle on N close to phi 0 and phi product. Now, I've been incredibly vague here. What does it mean for phi twiddle to be close to phi 0 and close to phi product? One could be very precise and write down lots and lots of estimates, but it would take quite a lot of time, and so I decided not to bother. So I won't care about making this statement precise, but I do want to give you an idea for how this is proved. And the proof idea goes as follows. So remember, we defined N using this map rho from, well, T3 times pi inverse of B4 mod plus minus 1 onto U. Now, what you could also do, if you were so inclined, is you could rescale the Iguchi-Hansen direction. So you don't change anything in the R4 direction. So you still use the identity on T3. But now you use the this projection pi down to C2 mod plus minus 1. But then you compose it with multiplication by t, say for some number t between 0 and 1. So what is this thing? This thing now is a map from T3 times pi 1 of not just B4, but actually T minus 1, B4, mod plus minus 1, onto the same set U as before. And if you do all this construction that I explained before, well, you get a manifold NT, and the picture above is still true. In one part of your manifold you have phi 0, the flat G2 structure. In another part you have the G2 structure phi product. And so you can interpolate between the two and get some G2 structure phi t. But as remarked before, you shouldn't expect this phi t to be torsion free, because when you interpolated between the two torsion-free guys, you made some error. So where you did your interpolation, it won't be torsion-free anymore. The picture for what's happening is the following. So we have our singular manifold here, T7 mod alpha, with the T3 there, and our neighborhood U here. And now say for t equals to 1, well, that's just our original picture. We have, oh, let's call this map rho t. So rho t is our rescaled version of rho from before. Well, for t equals to 1, we've seen that before, we glue in this green region here from the smooth manifold. But now what happens when rho gets smaller, say t equals to 0.5, is that we actually take a bigger set out of our smooth manifold to glue in. Maybe now it's this big already. So the yellow set stayed the same size, but the thing we glue in becomes very big, but we scale it down to get something of the same size. And so what happens when t is very, very small, say t much less than 1, well, our smooth manifold, this T3 times Higuchi-Hansen space, is non-compact, and the yellow set is bounded, so you're never going to get the whole non-compact space, but you're going to get an enormously huge set out of your T3 times Higuchi-Hansen space. Something like this. Alright, so what was the point of doing all of this? Well, remember what we know about the hyperkähler triple on Higuchi-Hansen space. So we know on XEH that omega I twiddle is approximately equal to omega I, where omega I is the flat hyperkähler structure and omega I twiddle is the hyperkähler structure on Higuchi-Hansen space. That's at least true far away from pi inverse of 0, far away from this exceptional locus. But what you will find is, if you go through the definition of phi product, you will find that on T3 times XEH, phi product is approximately equal to phi 0, the flat G2 structure, far away from T3 times pi inverse of 0. So what's happening is you're gluing something into your orbifold that at the boundary of this gluing area looks very similar to the flat G2 structure. So that means when your T is very small, the interpolation error that you make is very small, because you're interpolating between literally the flat G2 structure and something that looks very similar to the flat G2 structure. And you can quantify this. You can check that nabla phi t, where it's not going to be literally equal to 0. If it was exactly equal to 0, then you would have found a torsion-free G2 structure. But it's pretty small, so one way to express this is measured in the C0 alpha norm. You will find that this is bounded by constant independent of t, times t to the 4. So as you make your t very small, you can make it as small as you want. You can make the arrow as small as you want. And now maybe one of the main parts of Joyce's paper was the last step. So I unfairly sum this up with one arrow, and I write elliptic analysis. And the end result is that for small t, there exists some 2 form such that phi twiddle t defined to be phi t plus d eta t is torsion free, in the sense that nabla phi twiddle t equal to 0. Now, as I said, I may have made it seem easy because I just wrote arrow, but in fact that's a very difficult argument to make. But it's not the main focus of the talk, so I'm not gonna spend any more words on that. But either way, you do end up with this neat torsion-free G2 structure phi twiddle t in the end, and you can't write it down explicitly. You don't know so much about this eta t, but what you do know is that eta t is small in a suitable sense, so your final phi t twiddle is kind of close to the original phi 0 and phi product.